Hi everyone, this is Gautami from Sri Venkateshwara College of Engineering. Today we'll talk about a topic from ADA and we'll discuss about the Kruskal's algorithm. So moving on to the topic, introduction objective. To understand the Kruskal algorithm and its application in finding the minimum spanning tree of a graph. So what are the topics we'll be covering is overview of Kruskal's algorithm description, example, time complexity of the Kruskal's algorithm and its applications. What is the problem statement in this? Given a connected undirected graph with weighted edges, find the minimum spanning tree of the graph. We are supposed to find the minimum spanning tree of a graph. So definition, what do we understand by a minimum spanning tree here? A subset of edges that connects all the vertices with the minimum total edge weight and without any cycle is known as a minimum spanning tree. And our aim of this algorithm is to achieve this minimum spanning tree. Kruskal algorithm overview approach. Greedy algorithm that builds the MST, that is minimum spanning tree, by adding the edges in an increasing order of weight, ensuring no cycles are formed. And this will be having weights which can be taken as the additional amount or the value which is given to each edges. Steps. Sort all the edges in a non-decreasing order of their weight, that is in increasing order. Initialize an empty set for MST. Add edges to the MST using a union find data structure to check for all cycles. Stop when there is an edges in the MST, where VVV is the number of edges. That is, we'll be checking if there is a cycle to finding the union. Because we know when there are two sets and you do union of it, it's supposed to be the original set. If there is something missing or if there is something alternative which has been repeated, it is said to be that there is a cycle being formed because the edge has been repeated twice. Algorithm description, step-by-step process. Sort all the edges in a non-decreasing order based on their weight. Initialize. Create an empty MST and union find data structure to track the connected components. Progress edge. Integrate to the sorted edge list and add the edges to the MST if they do not form a cycle. Then connect the two different components. Completion. Repeat until the MST contain the V-1 edges. Union find data structure helps in efficiency checking and merging the components to avoid the cycles over here. So we'll see an example. Consider there are 4 vertices. So if there are 4, so that is 1, 2, 3, 4, and we can see that there is an edge from 1 to 2, 1 to 3, 1 to 4, 2 to 4, and 3 to 4. So we can draw a graph by drawing the vertices and connecting to it. And there being weight also being given, that is 10, 6, 5, 15, and 4. The second step is to initialize this. So we'll be initializing. So we know that there are 4 vertices. So we are given 1, 2, 3, 4, which contains the union of it. So the process is that we are going to add these edges in a decreasing order. So that we'll be selecting only one by one of the edges and will be forming the graphs, and will be also be checking concurrently or the parallelly that if there is any cycle being formed. According to that, we'll move on to the previous slide and see. So if we go from non-increasing order, the first one will non-decreasing order, the first one will be 4, followed by 5, 6, 10, and 15. So we'll first check through 4, if there, and then we'll draw the fifth one with the 5 weight which contains the edge. And then we'll make sure while doing the 6th weight, we'll make sure there's no cycle being formed. If there is no cycle being formed and all the edges are included, then that will be the minimum spanning tree. So according to this is the minimum spanning tree, which has 3 edges and the weight of there are 4, 5, 6 respectively. And what is the time complexity of it? Time complexity analyze. Sorting edges, that is we go to the log E and we go E by log E and we go E log E. Union find operation will be having where V is the number of vertices. Overall time complexity would be this. And what about the space complexity? Space complexity is nothing but the memory takes memory of the data which is being allocated, so that it is very efficient for us to maintain these two, the time and the space complexity, because the algorithm efficiency will be effectively regarded on these two components. So what is the applications of the Kruskal algorithm? Use cases, network design, infrastructure, and clustering. Network design, designing efficiently communication networks, such as minimizing the cost of laying cables, infrastructure, construction, road, pipelines, or other infrastructures with minimum cost. Clustering in machine learning for clustering algorithm like hierarchical clustering. For example of the applications are telecommunication networks and road networks. Telecommunication network, minimizing the cost of connecting cities with fiber optical cables. Road networks, planning the network of roads to connect town with minimum road length. So this was the application. We saw what is Kruskal's algorithm, what is the problem solving statement in it. We saw the steps how we need to solve the algorithm, and we even saw the algorithm and we saw an example how it needs to be solved. Later on, we saw the applications of it wherever it is used, and the time complexity and the space complexity were also being discussed. So this was a short about the Kruskal's algorithm. I hope it was useful. Thank you for watching it.